Hello everyone, my name is Gennady Gor and I'm going to talk about density functional theory model for adsorption-induced deformation of materials with non-convex pore geometry. And first of all, I want to introduce the first author of this work, Dr. Andrei Kolesnikov, who is a researcher at Institute for Non-Classical Chemistry in Leipzig and who has been a research scholar with me. Thanks for the German Academic Exchange Service. And I also want to mention that the work I'm presenting today has been published recently in Journal of Physical Chemistry C, so all the details can be accessed there. All right, what is adsorption-induced deformation? Well, this is quite a ubiquitous phenomenon when porous materials adsorb fluids and change their shape. They expand, they contract. It happens for all materials, and the smaller the pores are, the more pronounced these effects are. And a typical example of adsorption-induced deformation is a pine cone. When it's humid, the pine cone closes. When it's dry, the pine cone opens. And this picture, well, this is actually not a real pine cone. This is an artificial pine cone made of porous silica, which behaves similarly to a real one. Therefore, an adsorption-induced deformation, which is a contraction or expansion of material due to adsorption, well, has a potential for applications for smart materials such as sensors and actuators. And I want to mention that this work was funded by National Science Foundation, and thanks to them, we're able to do this research. All right. Well, in general, when we study adsorption, we typically deal with pretty simple pore models. We assume that the pores in materials are either spherical or cylindrical or have slit-shaped pores, and these type of models have existed for many decades. And typically when we get, for example, the pore size distribution of materials, we assume that this material is composed of, let's say, spherical pores or slit and spherical, but rarely go beyond these models. However, there are many materials where the geometry of the pores clearly don't fit to one of these three categories, and in particular the CMK3 carbons, which are templated from from silica with cylindrical pores, but their pores are essentially these cylindrical rods organized in these hexagonal lattice. While obviously adsorption on the surface of a rod is quite different than adsorption inside a cylinder. And however, well, in the literature, typically adsorption in these type of materials is represented with cylindrical pore model. Also, I want to say that although CMK3 carbons have been around for 2 decades now, recently there was new development into the hierarchical templated mesoporous carbons, where on a micro scale they have the structure similar to CMK3, but they're synthesized as monoliths, and they're composed of these carbon struts. So we're hoping that this theoretical model will help understanding adsorption in these new types of materials. All right, so when we look at nitrogen adsorption in CMK3 geometry, well, typically, as I mentioned, it's represented by a cylindrical model. Furthermore, it does a pretty good job with getting the pore size distribution. And I want to mention that about a decade ago, we wrote this paper where we developed the DFT models for CMK3 carbons, specifically based on a cylindrical pore model. Well, our goal here is, however, to develop a DFT model for gas adsorption on CMK3 carbons using a more realistic pore shape, and furthermore develop a DFT model of adsorption-induced deformation of these type of materials. So the method is the classical density functional theory in the local approximation. The idea of this method is quite straightforward. We consider the grand thermodynamic potential of the fluid, omega, which is a functional of the fluid density in the pore, and represent it as the free energy plus the term related to the interaction, the fluid-fluid interactions minus the term related to the chemical potential. And then in order to find the optimal potential, we need the optimal density profile. We need to minimize these potential with respect to the density profile, or to solve the earlier Lagrange equation here. So F, the Helmholtz free energy, is given by the two terms, while the ideal and the excess term, and the excess term is, well, that's sort of the main challenging part of the theory, obviously. So we consider it as the hard sphere term plus the mean field attraction term. While the reason we considered it in this simpler approximation is because the geometry is complicated. The problem is two-dimensional, unlike the cylindrical or spherical or slit pore, and solving it with a more advanced DFT would be technically quite challenging. Furthermore, we approximated the fluid-fluid interactions with the square well potential, and while the solid fluid interaction, however, was approximated with the Lennard-Jones potential. And Lennard-Jones potential in this case was integrated over the area of each of these rods. So this is this is the system we consider, and in fact we don't need to consider the entire system because of the periodicity. We consider this red triangle here. This is the small domain where we solve the problem to find the optimum density profile. However, in this domain, we consider also the effects from other rods, not just from this rod, but from the neighbors as well. And the solid fluid interaction potential is given by this expression, well, used previously in works on molecular simulation, for example. There was a recent paper with grand canonical Monte Carlo simulation in this system, taking into account the geometry. So the key thing here, since we introduced a simplified fluid and solid fluid potentials, the key here is to fit the parameters from the experimental data for the fluid to represent nitrogen with a square well fluid, right? And we got these parameters fitting the experimental data, which, well, provide us with pretty good fit. And then we, using these parameters, we solved this equation for the density profile, solving it iteratively. All right, well, that's about modeling the adsorption. What about the deformation? Well, typically deformation is described within the simple concept of Solvation pressure and Hooke's law. In addition to that, well, we follow this approach here, except for, we take into account this geometry. So we assume that our rods are connected with some springs, and the deformation takes place only in the normal direction, so in the direction in the plane of this picture here. Then we write the thermodynamic potential for the ensemble, taking into account the elastic free energy given by the Hooke's law here, and then minimize it with respect to the spring distance and get this equation for the sought Solvation pressure. Well, to compare it with a simple cylindrical case, which has been done years before, well, that's how the solvation pressure looks for cylindrical case. And before showing the results for our hexagonal geometry, I'll show you the results for the cylindrical pore. So the cylindrical pore provides our calculations using our model with the same parameters for cylindrical pore, gives very reasonable results for both adsorption isotherms in the range of pressures and for the solvation pressure and the deformation. So the adsorption isotherms are consistent with earlier works, and the solvation pressure is also consistent. And we can see here the two regimes of deformation: the Banham expansion here in this first part, and then the expansion due to the decrease of Laplace pressure here. And I'm not going to go in details discussing this because this has been all published well about a decade ago in my work with Alex Neymark. So here are the results for our CMK3 pore. The isotherms look qualitatively different, so do the solvation pressure curves. So first of all, on the isotherms, we have two hysteresis loops, right? One here and one here. And on the solvation pressure, we have also three regions. First, we have no deformation here. Second, we have contraction, and then continuing contraction, and then expansion due to the Laplace pressure. I want to emphasize that this part of the isotherm looks exactly like the corresponding part of the solvation pressure isotherm for cylindrical pores. So what's the mechanism here? And I'm showing here the density plots for these calculations. So in the initial region here, we have adsorption on our surface of the rods of thin liquid films, right? So polymolecular film is growing here. Then at this point, and let me consider, for example, the red curve. At this point, the first capillary condensation takes place. Well, the pores are not entirely filled, but the liquid bridges, these green density plots you see, these bridges form between the adjacent rods, and then the bridges become thicker, and then at even higher pressure here, the second capillary condensation takes place. Now the pore is completely filled with a capillary condensate. So if we look at the solvation pressure isotherms, it's well, we can interpret what's going on here. So when we have just the polymolecular films on the surface of the rods here, obviously these films cannot contribute to the normal deformation in the system. They don't deform the system in these planes. So the Banham effect is totally absent, right? We have the flat curve here. Well, in the second region here, well, after the first phase transition, we have this liquid bridge which pull the rods together. Therefore, we have these contraction here and further continuing contraction when the size of these bubbles decrease. So the smaller bubbles will cause more contraction. And then we have a second capillary condensation, another contraction, and then after that, the curve goes up because we increase the chemical potential, and this curve goes up as a log relative vapor pressure, similar to the case of cylindrical pore. All right, with that, I'd like to conclude. Well, first of all, the local DFT is a suitable tool for predicting adsorption and adsorption-induced deformation in complex pore geometries, where, well, the non-local DFT become too challenging computationally. In CMK3 carbon materials, bridge formation changes both the adsorption isotherms and solvation pressure. Solvation pressure shows a trend qualitatively different from the cylindrical pore model. The model can be extended to other materials with non-convex pore geometry, and in particular silica colloidal crystals in other materials in which The pores are formed by the spaces between the spherical grains, and this work is currently in progress. And I'd like to emphasize once again, well, this work has been published and available on the ACS website. Thank you for your attention.